day and welcome to Mad Report Weekly, where numbers tell real world stories. I am Muhammad Harikh reporting from our virtual studio. Today, we are putting the spotlight on one of Southeast Asia's smallest but wealthiest countries, which is Brunei Darussalam. Brunei is a sovereign nation located on the island of Borneo. Though small in size, it is rich in natural resources, especially oil and gas, and is known for its high standard of living and peaceful society. But what makes Brunei even more interesting in our study is in its population. Over the last 2 decades, the country has experienced steady growth with minuscule disruption, making it in the perfect case study for mathematical modeling. In this project, our team is using differential equations to measure the population growth in Brunei. By analyzing population data over 2 years, we aim to develop a mathematical model that doesn't just fit the past, but also predict the future. Through this approach, we will explore how mathematics, especially calculus, help us understand real-world trends in society. So, is math really useful outside the classroom? Let's find out, starting with the data. Now, we will pass it over to our next reporter, who will walk us through Brunei's population data. Please, Haqimi.
Thank you to Mr. Harikh for a wonderful introduction. Now, let's start simple. Let's move to calculation part. Good day, ladies and gentlemen. Today, I'm presenting a report that connects real-world data with mathematical modeling. This time, focusing on population growth of Brunei Darussalam starting from the year 1970. According to historical data from Data World Bank, Brunei population in 1970 was just over 129k people. Over the year, this number has steadily increased. We can refer from this table. The resources said the number of population in Brunei Darussalam has rapidly increased over the time, which make the graph look directly proportional. To analyze this growth and project future trends, we apply a mathematical approach using differential equation. In our model, we assign t equal to 0 to the year 1917, which this timeline help us study how the population change annually and allow us to model the rate of growth mathematically. We use a differential equation of the form dp over dt equal to constant proportionality multiplied with population, where p is the population, t is time, k is a growth constant. This equation model exponentially growth, which is often used to represent population increases. By analyzing the data and estimate the growth constant k, we derive a predictive model pt equal to p naught exponential power of constant multiplied with time. As we can see from part of this work, we integrate them to get our general solution, which is this, and we use t equal to 1 represent the year 1971 and equal to the population of 135,671 human, and then we can generate from that to get our particular solution. Then we can find our experimental value for each year to find the expected value for population human in Brunei Darussalam, and then we can compare from the value and then get this table, which is to show us now. End of this part. This type of model is more than just mathematics. It's a valuable tool used by government and planner to forecast change, manage resources, and make informed decisions. In conclusion, this project highlights how mathematical equation can reflect real-world behavior with data analysis and little calculus. We can tell the story of the Brunei growth through time. Now, and the part of my session, and I will hand this to Miss Joyce.
Thank you, Mr. Haqimi. Using a particular solutions that has been calculated, the estimated population in the year 1969, which is the past value, is 123,665, which is lower than 1970. Using the same formula of the particular solution, the estimated population after 10 years is 205,858 people, which is we can see that the population in Brunei is increases every year. But there is a difference between actual value and the value that have been calculated just now. So why? My friends will help to answer that question.
So I'm going to answer the question why there's a different value between actual value and predicted value. First, we look for value for the year 1980. The predicted population was 205,858 people, but the real value was 193,879. So the prediction was not accurate with a different 11,979 people. From this difference, we calculated percentage error of 6.12%. Why was there a difference? This may be because the prediction model did not include real-life factors like health issue, accidents, or economic change. So in 1970, fertility rates were higher, which led to more population growth. Women were expected to have more children during their lifetime. By 1980, fertility rates began to decrease due to several reasons. First, higher mortality rates, including maternal death related to childbirth, especially for women aged 40 to 15. Second, poor healthcare, as medical facilities were not advanced at that time. Third, disease like malignant neoplasm, cancer that can cause death. Last but not least, accident, also including accident roads and other, were major causes of death. So what will affect future growth? COVID-19 is one big factor that affect health and may change the population in the future. So back. So now let's back to our main reporter, Harikh.
Thank you, Alya. To wrap up, we explored Brunei's population growth using differential equations. Starting with 20 years of real data, we created a mathematical model, visualized the trends with graph, and made predictions about the future. This project showed us how maths working, especially differential equations, can help us understand real-world patterns, not just number on page. In the end, we show you the task too that presented by Mr. Asyraf and Mr. Hariz. Thank you for watching, guys, and remember, math is everywhere. Have a good day, everyone.
I will be presenting our task 2 assignment, which is the Simpsons rule. So moving straight into the question, the question wants us to integrate y equal to x power of 3 plus 5 over ln in bracket d plus 2x squared from x equal to 0 until 11.5 using the Simpsons rule with 5 and 9 ordinates. So we will do the 5 ordinate first. So the first step is to find the change of x, and change of x is denoted by b minus a over n, where n is the subinterval. So our b is the upper limit, and the upper limit is 11 over 5, which will turn into decimal number, become 2.2. A is our lower limit, which is 0, and our subinterval equal to 4, because we subtract 1 from the ordinate, which is 5, so 5 minus 1 is equal to 4. Next, we're going to make a table consisting of 4 columns: x, fx, coefficient, and coefficient time fx. For the x column, the first row is going to be our lower limit, which is 0, and every time we move to the next row, we're going to add our change of x all the way until our upper limit. For the fx column, we're going to substitute all the respective x value into the equation. And for our coefficient, the first and last row of our coefficient is going to be 1, and the row in between them is going to be alternating in between 4 and 2, starting with 4. For our coefficient time fx column, we're going to multiply the coefficient and fx of the same row, and then we're going to sum all the coefficient time fx, and we will get this. So with all the information that we have get, we're going to substitute it into the formula, which is the formula of Simpsons rule. Our change of x is 0.55, and the one that is in bracket is actually equivalent to the sum of the coefficient time fx, which is this. So when we substitute all the value into the formula, we're going to get the answer is 9.9444819, which is close to the actual value, which is 9.9619484. So next, for the 5 ordinates, we're going to do the same thing, but the only thing that will change is going to be our subinterval, which is going to be 8. So when we substitute the value into the change of x, we're going to get 0.275, and then we're going to do all the same thing like the 5 ordinates, and the answer is going to be 9.9616559. which is more closer than the 5 ordinates. So we can conclude that the more ordinate we use for the Simpson's rule, the more accurate the value is going to be the actual value. So that's all for me. I'm going to pass the presentation to Asyraf to explain about the graph.
So for the graph, we can use Desmos to generate our graph. So for this test, sub-intervals. For the first graph, there are 4 sub-intervals, and for the second graph, there is 8 sub-intervals. We can compare the graph that we have generated. As the sub-interval increase, they are more accurate than approximate value, but this value is not a real value, but just a approximate value. They are more accurate to the real value. That's from me. Thank you.